Just a quick mention for Team 5. You're the only ones that haven't scheduled anything with me this week. So basically, you have to do it at 1:30 today. But because that's the only time I have time left in this week. Because I have 4 hours of lecture now, because I have one lecture with you and then one lecture with Norwegian students. Then I have 2 more meetings. So then I have time for Team 5 in a meeting. And tomorrow and Friday is 6 hours of lectures in a row, so I'm going straight home afterwards, just to try to relax my throat a bit to survive. So we have we saw the clip here with the solenoid valves as the last thing on Friday, and it's basically exactly the same as a regular valve, only you have electrical controls, and you're using electromagnets inside here to actually push on the piston lever, on the piston rod. It's basically the exact same, only you have added another element of technology to it instead of actually pushing on it. So we're going to look at some performance data for 4-port solenoid valves with 3 different switching positions. So then we have a really big table to look at. So all of these are surface-mounted ones, and these NG codes, those just stand for the location of the portholes when you have a surface-mounted one. So remember before the clip, we looked at these different setups. So we looked at the NG10 and the NG6, and here in the table we have NG4, NG10 and NG16. So they're just different setups for where the ports are located, basically. It doesn't really matter much for this course with the port setups. It's more when you're actually designing something and you're choosing your valves, you need to have the ports matching up to each other. So you need to know that there's a difference between these, so that you can put an NG4 port onto an NG10 port, so you can't match those 2 up. So if it's a directly actuated solenoid valve, we have this symbol, and in this case we have solenoid on each sides. So we have the solenoid symbol there, and this one has also gotten those centering springs. So it's got a spring on each side, which means that when you're not supplying electricity to one of the solenoids, it's going to end up in this mid position. So it's just going to stay there because the springs are going to push against each other, and they're the exact same kind of spring, so they're giving the same amount of force, so they're going to just stabilize it in the middle. That also means that if you want to switch it to have it in this location, so that you're getting your pressure delivered to port B and you're getting return from port A to tank, then you have to apply electric current to this solenoid, and you have to keep applying it in order to keep it in place, because as soon as you let up the electric current, the springs are going to push it back into the middle, so that it's sort of a fail-safe for this one, that it's going to close off as soon as it loses power. The same goes for the one on this side, but this one is pilot actuated, and that's the reason why we have these black arrows on the sides there. They're to show that it's pilot actuated. So this is most likely then a really large valve, which we sort of get confirmed by looking at. We've got a higher port specification on it, so that most likely we could see the NG6 was smaller than the NG10 pattern. So the NG16 is larger than the NG10. So we are getting larger and larger in the basically just in the size of the valve here. And what's often done then when the valve becomes large enough, it requires quite a lot of force to move it, and then it's often easier to just activate a much smaller valve. And when you activate that valve, it lets in pilot pressure on this side, which forces the slide over. So you're just utilizing the hydraulic pressure in the system, and you're pushing the slide over by that one. And you're using a different, smaller valve to direct this pilot pressure. So we're going to look more at that in the next lectures on how these pilot systems work. But what we looked at up until now with those pilot systems is that they're basically dumb. So they only work on reacting to pressure. Because we looked at the pressure relief valves and everything, and those are directly connected to the pressure. So they're directly reading off the pressure and activating once the pressure reaches a certain level. But these ones are only activated once you hit in electric current for the solenoid. That's the only time you are letting the pilot pressure in here. So that it's a more of a manual process of telling when to open and when to close for it. And still it has double springs, so that it's going to push back into the center whenever you let go of your electric current. So we can see that there's not that much difference to the maximum operating pressure, and that's from the pressure ports and to the A and B ports, so delivered from the pump through the valve and to the A and B ports. So you get 250 on the smallest one here and 320 on the rest of them. So it's even though it gets larger and larger as we're looking at these different kinds, they don't necessarily can handle more pressure, but they can handle more flow. So that it's a larger valve, so it has a larger cross section, so it can handle more flow through it. So that's usually the point of getting a larger valve, is just to have enough flow being delivered through it. And the maximum pressure when we are returning to tank, we can see that it's differing a little bit in the different kinds here, but all over it's lower on the pilot actuated one, and that has to do with the pilot pressure being connected to stuff here, because the pilot pressure also has to be able to return to tank and stuff, and then you can't really have too high of a pressure in the return line. Of course, there's no pilot pressure on this side, because this one is directly actuated. So on this one, the electromagnets inside the solenoids are working directly on the piston stem that's going on the piston rod that's going through the valve. So it's working directly on that one. But here we have, of course, the pilot valve that's letting through pressure. And as you can see, the pilot pressure is very small. You don't really need much pilot pressure in order to activate those. And that has to do with this being slide valves, because sliding the valve back and forth doesn't really take much pressure. And so long as you don't have a super strong spring there that's going to put a lot of force into it, you don't really need all of that much pressure in order to push it in either direction and compress the spring. But you can have quite high pilot pressures. So we have a minimum and you have a maximum on them. It just depends on how the valve has been designed with regards to handling pressure. If the pilot valve is a separate valve that's being put in, it might be one valve that has a very low pilot pressure capacity. While if it's built into the main valve, so it's a part of the housing of the main valve, it's usually built to handle more or less the same pressures. Usually a bit more, but more or less the same. And we can see the difference here in flow rates. So you have the smallest one, 20 liters per minute, and then 300 liters per minute for the largest one. So it just shows that even though the pressures don't really change that much, you can have quite a lot of change in the flow rate for each of them. And here we have some switching times for the solenoids. So they are direct current, so they're not alternating current like we have in the wall sockets in our houses. So they are direct current, the same as we would have in our if you have a regular car. You have direct current from the generator on the car is creating alternating current, but it's being directed into it's being transformed into direct current and sent into the battery, because batteries use direct current. They don't use alternating ones. So these are also direct current. So it's not possible to just plug them directly into your wall socket and make them move. They need to be transformed from alternating currents. Usually the transformer is built into the solenoid system. And you can see here, we don't really, it doesn't really take much time to energize them. So you have anything from 20 milliseconds up to 95 milliseconds So it's really, really quick to move these in. And you can see for the small one that is directly actuated, it's not really much of a difference between the pilot one and the directly activated one, even though the pilot one is larger. But when you go for the largest one on the directly activated one, which is, it has the same port signatures and it has roughly the same flow rate going through, it takes considerably more time to activate the one that's going directly on the solenoids. And basically just because the piston rod inside here and the pistons, they're larger, there's more mass in them, so it takes a bit more force in order to start moving them back and forth. So it takes a bit more time for it to react, basically. And that's why we're using the pilot operated ones, because then we get even quicker response times on them. And the same goes for the larger one, which is 3 times the flow rate from this one and still approximately the same response time on the solenoids. Then we have the temperature of the hydraulic fluid itself. So not really all that much of a difference. You can have it down to -20 on the large one, but you usually think from 0 to 60, 70 degrees. That's a very, very normal range to have on it. And then ambient temperatures, they're -20 to +70, more or less. So it's not really that much of a difference there. So actuation methods. So actuation is when we are actually moving the piston rod inside the valve. That's when we are actuating the valve. And there are quite a lot of ways of doing that, and it depends on our system requirements. So sometimes we might want to have a manually operated one. So we want an operator to be standing there with the lever and pushing and pulling, or pushing in a button and releasing the button. There are several ways of doing it manually and like that. It can also be mechanically operated. For an example, in a production line where you have loads of stuff going on, you might have one of these. One of the things that are moving along the tracks of the production line, it might have a sort of a rod sticking out of it, and that rod is going to push on a mechanically operated lever after a while. So it's going to push it in and actuate a valve that is going to open up for something else to start happening in the production line. So that's one of the ways of doing it, just having, if you already have something moving, you can have that activating valves as it's moving along into the correct positions. Then, of course, you have the solenoid actuated ones. And with the solenoid actuated ones, you can basically get the same effect as with the mechanically operated one. You can just put in a sensor that just senses when it needs to open up. So it looks at the production line moving past it, and then when it sees something in specific, it's going to react, and then it's going to open up the valve, or actuate the valve. If it's opening or closing it, of course depends on what's going to happen. And you can have loads of combinations of the above. And usually you have somewhere in your system, you're going to have a manually operated one, which is going to be a shut-off valve, which is going to be the emergency stop. In case something goes horribly wrong, or someone gets their hand jammed into somewhere where it's going to be crushed unless you stop it. So then you want to have manually operated buttons close by. And those are buttons that will, once you activate them, they're going to shut down the flow, and it's going to just stop. They're not spring operated, so they're not going to push back and open up the flow again. So you don't have to hold the button down. You're just going to press it once, and then it's stopped. Then you have to go over and manually pull up the button in order to open it up again. And I've seen systems where both solenoid and mechanical and these manual emergency stops have been integrated into the same system. Where there were some places in the system, it was actually easier to just use mechanical operation on it, because you had, in this particular system, you had a rotating ring, and you just use the cam principle, where you have raised ridges on the ring, and whenever it would rotate into the correct position, the ridge would start pushing on the mechanical lever for the directional control valve. And then you had other places where it was a bit different. They had cameras sensing the production line. So the cameras were looking at the production line and seeing if something was out of place. Basically, they needed the parts that they were producing, they needed to be positioned in a very particular way. Because when they were going into packing machine. So all of them needed to be placed in the same position so that they would all be packed in a line inside the crates. And they had a camera looking at them and sensing if they were in the correct position or if they had been turned somehow. And if they had been turned, it would activate a directional control valve. This was a pneumatic system. It wasn't a hydraulic one, so it was using compressed air instead of hydraulic oil. But it was still the same principle with the valves and everything. So what it did then was it was activate the valve, and the valve would push out a piston, which would enter partways into the path of the part that was moving along the conveyor belt. So it would hit the piston, and then it would be turned around. And then it would go to another sensor that would check, is it in the correct position now? And if it still wasn't in the correct position, another piston would be pushed in that would rotate it. And that was the extent of what they had. There was only 3 ways they could end up in there, and if it wasn't correct the first time and it wasn't correct the second time, it was going to be correct the third time. So they didn't need to have a sensor on after the second piston. So then it just went straight into the packing crates. So that was a nice way of seeing that they actually had different kinds of valves being operated in one system. So if we're going to look at the hydraulic circuit diagram, just to look at everything we need in order to see a directional control valve. So we need to know the basic actuation method, what's going to be the basis of it. Is it going to be a solenoid one? Is it going to be a manual one? Or is it going to be mechanical? We also need to know if there is a reset method. So are there springs? Is it spring operated? So it's going to be reset into a certain position once you stop actuating it. And is there any pilot control? So we need to know that also. So that's why we have all of these symbols on the sides of the valves. And it is also possible to put in additional actuation options. For an example, if you have the solenoid symbol and then you have above the solenoid symbol you have the spring symbol that's going to return it to the original position, then you can have above that one again, you can have a push button for an emergency stop, for an example. So it's possible to have it in many different things, many different actuation options in one single valve also. You don't need to just combine them in one system. And of course, we've already seen that the symbol is located next to the switching positions in the boxes on the field, but it also is that the actuation symbol is located next to the switching position that it's going to switch to. So that when we have an example on the previous one here, we had a 4-3-way valve. And then we have solenoid on each sides and the springs. So if we activate this solenoid, then it's this one that's going to be engaged. So this switching position. In the previous case, we had closed off in the middle, and we had cross flow on that one, and we had direct flow on that one. So if we activate this one, put electric current on that solenoid, it's going to switch over to this one. So then we are going to get our ports connected over here instead, as long as we are putting electricity onto this one. And if we put electricity onto this solenoid instead, we of course are going to activate this switching position. Yeah. So we have many different symbols for showing how we are operating or actuating the valves. So you can have a push button where you are just pressing on the push button, basically, a manual operation. You can also have a lever. So for an example, in the case of this valve, if we have a push button, we're going to have a push button on both sides. Because if you want to activate this switching position, you're going to have to push the button on this side. And if you want this switching position, you're going to have to activate the push button on that side. So usually when you have just a single push button, it's usually just 2 switching positions that you have. So it will either be closed or having flow, or that you are changing between 2 ways of flow in it. So you will just have the 2 positions to choose from, which is why push buttons are often used for emergency stops, because it's very easy if you're working on a system and you know you have a push button on the table beside you here. If something goes wrong, you can just slam your hand on it, and then you've stopped the system. And the valve that's being run by the push button will most likely be one of these. So they will, unless you are activating it, it's going to be allowing flow through, and once you activate it, it's going to close itself off. So you'll just have 2 switching positions in it. However, if you have a lever, then it is fully possible to have the lever just on one side. Because it's going to be possible to push your lever forward into this position, or you can pull it back into this position. So that means that if you push it forward, you're going to push this one over to the middle so that you're going to activate this switching position. If you pull it back, you're going to pull everything towards you so that this one is the one that's going to be activated. And then if you have it just in the center position, you have the center one. So with a lever, you can actually do everything from one side, basically. And with mechanical operations, you can have what's called just a stem, which is basically just a rod that's sticking out of the valve, and it's going to be pushed on with some mechanical motion going on in the system. And that motion is going to start pushing on the valve, and it's going to pushing on the stem, and it's going to actuate the valve. And you can also have a roller. So if you have something that's going to move past here and at the same time push it in, then it's nice to have a roller, because then you just have a rotating element on the edge there, just basically a wheel, which means that if you have something that's pushing directly on the stem, that's okay, because the stem is just moving into the valve. But if you have something that's moving past it and at the same time moving towards it, then you're going to start pulling on the stem. But with a roller, it's just going to roll on the wheel, so it's not going to have any pulling action on it. So it's a bit easier. Basically, if we have the stem here, you're basically looking for something to just move in here and push it this way. But if you have a roller, let's see. But if you have a roller instead, you can have, for example, the edge of a plate, and the entire plate is moving in this direction. And as the plate is moving down, this edge would start pressing on the wheel, which will start rotating, and it will start pressing the roller into the valve and start actuating the valve, basically. But if you did this option with just a stem like this, it would experience forces in this direction and in this direction. So you would start bending the entire stem, and that wouldn't be good. And then, of course, we have solenoid actuation. And usually what you've seen until now is to have one solenoid on each side to be operated. But it is possible to get the same effect as with the hand lever, and putting in, then you just put in one extra line on the solenoid system, basically. Then you can have the solenoid just on one side, and it's going to be able to operate in both directions, because then it's going to be able to both push and pull on the piston rod inside. And then you have combinations, like in this one where we have solenoid and it's pilot actuated, and we have manual overrides up top. So you can see that there's a push button placed in there, the same one as up here. And then we have the solenoid and we have the pilot actuated one. And in this case, they have the same effect on both sides for it. And then you have the purely mechanical components located inside the valve. We're still showing the symbol on the outside of it to show that it works as an actuation method, but the springs are located inside the valve usually, so you can see the springs on it. So you basically just have to know that it's a spring-operated valve, especially if it's a solenoid one where you can't actually push and pull. If it's a lever-operated one and it has a double spring return, so that it's going to be pushed back into the central position if you let go of the lever, then it's easy, because then you'll just pull on the lever and you'll let go and you'll see it's going to flip back into the central position. So then you know that this is a spring-operated one. Then you can check that it's a double spring-operated one by pushing on the lever and letting go, and then you'll see that it pops back into the original position, and then you know, well, we have a spring working in both directions. But if it's a solenoid one, you don't have any mechanical ways of pushing or pulling on it. You have ways of figuring it out, but the best way is just to look at the markings on the valve and see that, and the symbol, if there is a spring symbol on it or not. So that's the easiest way. Because usually, when you're buying a valve, you usually know what valve you're buying. But if you're using an old valve that's been in a warehouse for a while, so you're not quite sure, maybe it's connected to an old project. It's been in the warehouse for 5, 6, 7 years maybe, and then you're not quite sure, is this the same valve that it says on the papers in this old project, or is this a different valve? Did they not do the paperwork correctly? Could this be the incorrect valve? But usually the suppliers mark the valve housing in some way with the symbol of the valve, just to show what type of valve it is, so that it's going to be possible to actually look at the housing itself, try to figure out, and most likely it's going to be hard stamped, so that it's struck into the steel of the housing, and so that it's not possible to, it's not just on a plaque that's been glued to it or screwed onto it that could be lost in some way. It's usually into the material itself. So it's a nice way of just looking at trying to figure out what it is. So we're going to look a bit more at manual and mechanical actuation. And the control valves can be actuated by the means of a hand lever and manually switching. So in the case of what's up there, we don't have a spring return on it. So in that case, we would be manually switching between them, and it's just going to stay in its position. That's another thing that we're going to get to, is one of the things that wasn't mentioned in this one is the detent that we've talked about a little bit. And if you remember the symbol for that one, that symbol is usually placed in the same location as the spring symbol, and it's usually looks a bit like this. And what it just means is that once you've switched it into one position, you have a mechanical system in there that's going to keep it in that position until you actually apply some amount of force to the lever. So it's not enough to just accidentally poke it a bit with your finger. It's not going to switch at all. You actually have to use some force in order to get it in the correct position. So that one's not mentioned here, but we're going to get more into it in one of the, I think it's the next lecture. There is a very good where we're into a detailed view of it so that you can see actually what's happening in the detent when it's working. So mechanical one, we've already looked at the stem and the roller, and it also mentions trip cam, cam disc. So a trip cam, that would be more like the plate here, where we have a moving plate and it's going to activate the roller. A cam disc means that we have a disc with cams on, and it's going, as it's rotating, it's going to have edges that are going to push on the roller as it's rotating. But you can also have guide bars, and that is more like the one we pictured here on the stem. That's just going to push on the stem. So if you have a stem or a roller, you really need to have something else mechanical that's doing the operation for you. And then, of course, you have the spring option, where you just keep it back in place, switch it back into a neutral position, basically, unless you are actuating it intentionally. So then we're going to look a bit more at the solenoid ones. So they use electro-hydraulic controllers. So they use two forms of energy in order to control the valve. So it uses the electrical energy as a control signal, and it also, the electrical signals actuate the solenoid one, and then the hydraulic energy is distributed through the valve afterwards. So you're using electrical energy to distribute hydraulic energy, basically. And you use the electrical energy to choose which of the ports you are going to distribute the hydraulic energy through. But in the solenoids, we of course have potential for things going wrong, much more than just with a lever being hand operated, or a mechanical system for that matter. There's a lot less things that can go wrong in a mechanical system than in a electrical system. That being said, that doesn't mean that the electrical system fail all the time, because they are usually very reliable. So that's not a problem at all. But you just have more places where things can actually go wrong in it. For an example, you have the one that's completely out of your control, which is a total power failure. So if the power grid for the entire town goes out, then of course nothing's going to work, because it's electrically controlled. So you don't have any electrical energy to run it. If this is critical, so in your facility, it is very critical that you don't have power failures, then your facility is for sure going to be equipped with a backup generator. So as soon as power fails in the main system, the backup generator is going to kick in and start producing energy just for your system. That is usually a diesel or gas plant or something like that, placed inside your factory somewhere. But you also have more close to possibilities, like the wire breaks. So if you just get a wire break inside your system somewhere, it's a bit more difficult. Then you really need to go in with experienced technicians and try to start figuring out where exactly is this wire break, because it's not always possible to actually see where a wire has broken. If you can see a wire that snapped, then that's okay, because then you know that's the wire. That's the problem. But it might just be that a wire in one of the connections has a bad connection, and that's really difficult to see if you're not experienced and know how to do the search for failures in it, basically. So the system should be designed so that everything is undamaged, even though you do get a power failure. And that's often why we use spring returns on our system, so that if we have a solenoid-controlled directional valve, so we have one with, maybe it's solenoid control on both sides, and it has spring return, like in this case. Because then we know that when we are activating it to run our system, we are allowing flow through it, and our system is running. But we also know that if this happens uncontrollably, so that if we have switched in this position, to run a hydraulic motor anti-clockwise. So it's going anti-clockwise. And we need to, at a certain point, switch it in the other direction so that it's going to run clockwise instead. And that is very important for us to manage to do. It is better that we just stop everything if we can't switch at the correct opportunity. So if you then have a power failure and you can't switch it, then you're stuck there if you don't have the spring return. But if you have the spring return, you know that as soon as you lose power to the solenoid, it's going to switch into the middle position and it's just going to stop. So then the hydraulic motor is just going to stop its work, and everything is ready for when you have fixed the problem and you can start up again. So that's one of the reasons why we use these spring returns with closed valves, with a closed valve in the center position. So there are several ways of doing this. If we have a 3-2 way or a 4-2 way, so just 2 switching positions, but 3 or 4 ports, you can switch to a neutral position by spring return. So I'll just draw this one in here. So if you just have a 2 position one, so then you can have well, the spring return will be on this side, of course. And it might be closed off here, and it might be allowing flow when it's activated. So then you know that as soon as you lose power to the solenoid, it's just going to close off the entire valve. Or you might want it to return the system to the original state. For example, if you are extending a piston, when you're activating the solenoid, then you're extending a cylinder, the piston of a cylinder, and then you want it to, if something goes wrong, you lose power, you really want that piston to be retracted, so that the cylinder is going to go back to its original position. Then you can choose to have it on the return, using the return flow on the spring return there. So that once you lose electrical current here, the spring is going to switch it back, and you're going to reverse the flow for the cylinder, and it's going to be retracted. So then you are back into a safe position. So there are different ways of doing this. So it doesn't necessarily have to be that you're shutting down your system when you go into the fail-safe, but it depends very much on the system, what you can allow to happen. So for a 4-3 way, the one we have up here, the springs are going to center it, of course. So then we just need to think about what's going to happen when we are centering it. Do we have a pump that's being run on a different power system? So, for an example, is the pumping run by a separate diesel engine or something like that, while the solenoids are pulling power off the power grid? So if we then have a power failure, the pump is going to continue running. But if you shut down this one for a while, then the pump is going to be pushing with maximum pressure against the closed port here. So then you could have a problem. So maybe it would be better to have a loop here, so that you have your pressure port returning directly to your tank. Because then you would know that this pump is just going to stay there. It's going to pump. It goes 24/7. It always delivers hydraulic energy into the system. But in this particular part of the system, if we have a power failure, we don't want to block it off, because we want the pump to continue working, because then the pump gets no resistance. So it's basically if we disregard the resistance that we are going to get from the pipes and throttling points in the system, then you're basically going to have 0 bars of pressure going past here. You will always have something, because there is always a little bit of resistance in the system itself, but you definitely won't have 320 bars just being pushed straight into the valve and just staying there. It's just going to go in a circle instead. And then you have 4-2 way double solenoid valve. So we're back to 2 switching positions, and now it's a double solenoid. and it has a detent. Maybe have a bit more room between them. Now this means that if we lose power, it's just going to stay in the position that it was in when we lost power. So it's just going to keep that position because the detent is going to hold the switching position for it. Yeah, so that's basically as simple as that one is. It's just going to keep the position. So if you had started pushing out a cylinder and then you had a power failure, then the cylinder is just going to continue pushing out. So it's not going to be a huge problem. It's going to push until it reaches its end, and then it's just going to stop because then it doesn't get anywhere. So it really depends upon your system, what you can allow for. And then, of course, you have the possibility of adding manual overrides. And usually with either push buttons or levers that you can go in and manually override it. And that's especially if you have a wire break somewhere, so that your system is fully operational. It's just that one of your solenoids isn't working because there is a wire that's broken. So then you can have one of your operators come in and do a manual override whenever it's going to be run. We'll do a break, and then we'll continue on afterwards. Right, so there was actually one more point on this slide before we went to break, but I forgot it. So we usually use manual overrides during commissioning, so when we're building a system and designing it and testing out that it's working, or if a solenoid is failing, basically. So that's for the most part, so long as your solenoid is working and your system is fully operational, you're finished building it, then your solenoid is going to work also. And I think there's like a 99.98% reliability on most solenoids and stuff like that. It's really amazing how reliable they actually are. So even though we are looking at problems with solenoid valves, there usually aren't any problems with them. So that when you've got a system running, and so long as you're taking care of it and doing proper service on it when you're supposed to do it, then it's going to be fine. Now I was made aware of a bit further back here on the huge table that we had. Just not a bit, but quite a lot. So I've done a copy-paste error on the lowest one here. So it's the ambient temperatures in the book that are correct, not the ones on the slide. So I'm going to fix those before I release the slide on Fonto. So I can see I've copy-pasted this temperature, and then I've forgotten to change them afterwards. So it's just probably been interrupted while I was working there, and then when I got back, I thought I was finished with that slide, so I went on to the next one. So that's just poor checking on my part of my own work. So let's see, we're going back to where we were. So now we're going to look at two two-way valves. We're going to look at two two-way valves, 3 two-way valves, 4 three-way valves. We're going to look at quite a lot of different types of valves now and go more into detail on them. Because until now we've just looked at the symbols and how the flow is going to work when we are activating it in different directions and switching around on it. So now we're going to look at how did it actually work internally. So how does it work with the slide moving back and forth, and how do we gain the different functions from it. So on a two-way valve, we have one pressure port and we have one working port. So we don't have, since we just have 2 ports, we don't have a return to tank port on this one. And it is going to be either closed or open, because we basically don't have any more options on a when we just have 2 ports. You either close them or you open them up. You can't sort of direct the flow in the opposite direction or anything like that. So for a slide valve, it's usually looks something like this when we cut it open, where we have a pressure port, and then of course depending on how we want it to act, there is a certain amount of overlap here, either positive or negative or exactly 0. So depending on exactly which kind of valve it is. And we have the port going to our component. So if we activate this one, we push in the slide, then we're going to get full flow between this port and the component. And as you can see, we're going to have leakage past the pistons and into both on this side when we are activating it. That's going to move across here, and then we're going to get leakage line back to tank. But the leakage line is, as you can also see it from the cross section here. It's not made to handle large loads, so it's not something where you're not designing the leakage line to take a certain capacity. What you're doing is you're looking at the leakage line here, and it's been designed with regards to the expected amount of leakage past the piston, which isn't really much. A few drops here and a few drops there, basically. But there is going to be some fluid there, so you need to remove it from the system. And then you can have a poppet valve type for it, where you basically instead of just having pistons that are sliding back and forth, you have it's more or less a combination of a slide valve and a poppet valve, but it's called a regular poppet valve with regards to how it's located now, because here you will have pressure on the backside. The pressure will be pushing on the edge of the poppet, and it will be forcing it into the seat so that it remains completely closed. And the difference here is that once this one is closed, you have no leakage past the poppet. Here you will have leakage from P to A. So you are going to have a slight amount of flow going past there. But with a poppet one, it's completely closed, so you're not getting any leakage there. You will have leakage into the spring chamber and then out through the leakage line. There you will have it, because there is just a regular piston on that side. But here, since it's shaped as a poppet, it's going to close off completely. And the symbol is usually looking like this, where you have the spring symbol, and you have the leakage line going to tank, and then you have the push button on this side in this case. And if you activate the push button, then you're going to push this switching position over here so that you get flow between P and A. And as you can see, it says that you can have flow in both directions. But of course, if P is connected to your pump, then flow is, of course, just going to go from P to A. You won't have any possibilities of anything else. But if you are activating this one and your pump is shut off, then you can have flow coming back this way. So then you can have, for example, if you have a single-acting cylinder, which you've pushed out with, you've activated this one. The pump has been forcing hydraulic fluid in here. It's been pushing out the single-acting cylinder. And the single-acting cylinder also has a spring that's going to push it back if we stop it. So then if we just cut off the flow from the pump, then the spring is, of course, going to act on the cylinder, and it's going to push the flow back this way. So that's why it's going both ways in this case, because we don't have a direct return to tank on it. Most likely you would have another valve system further back that would allow for flow to return to tank somehow, that you would cut off the pressure from the pump and allow flow back to tank. It depends on your system. If it's just a very simple system, it might be that you only have this one. So yeah, it's basically just your imagination when you're designing a system, or what you're going to put into it. Some things will work, some things won't work as well. And my best tip, actually, when you get out into a working situation, if you're going to start designing hydraulic systems, is to get a hold of a hydraulics company that delivers hoses and components and everything. Get a hold of their service technicians, and basically get the okay from your own company that you can hire in this service technician to work a little bit with you. Because those service technicians, they usually have quite a lot of years of experience in working directly, physically on systems. And they see, basically they're going to know even more than you about the system. They don't know why everything is acting as it's acting, but they know that it does, so that if you put this valve along with this valve, then you're going to get this reaction out of it. You can look at it and you know the internal workings of the valve, and you know where the flows are going, and you know your fluid dynamics, so you know why stuff is happening inside it. But still, the service mechanic is going to, he's going to be able to tell you quite a lot of what you already know, and probably much more. So just getting a hold of these mechanics and technicians, and trying just to suck some of their knowledge for yourself while you're working. That's my pro tip for hydraulics, really. Try to work with as experienced people as you can when you're working, because you're going to learn quite a lot from it. Yeah. I'm not quite sure why it's larger here, but I'm thinking that it might be since you actually have a complete blockage here, you might end up with getting more leakage this way. I'm not quite sure if that's, I would have to really look into the fluid dynamics on it. It might just also be that they've, for some reason, They might have picked a larger valve so that all of the internal workings are a bit larger. They don't really explain what is what in the illustrations here, so we don't know if this is the same kind of valve and the same size. So it's a bit difficult to answer that one, but still you can see that the leakage line is smaller than both the pressure and component lines. So for the slide valve, when we are opening it up, we are pushing in the slide, so then we get full flow between the P and A ports. And now you can really see that we are going to end up getting some leakage over here on this side. And most likely what little leakage we do get when we have activated this one, that's just going to stay in this chamber while it's running, so long as we are actuating it. But as soon as we let go of this lever and the piston starts moving this one back, then you can see here it's going to go completely flush with the edge there. And then it's just going to force everything over on this side. So depending on if you have an old valve where it's been a bit subjected to wear and tear, so maybe you have more than usual leakage onto the behind the piston here, you might actually find that once you release the valve, it's going to move out. The lever is going to move outwards, and then it's just going to really slow down and then move the last part really slowly, just because it's trapping quite a lot of leakage oil here, and it needs to push the leakage oil through the leakage line. So it's just going to take a little while to evacuate all of that leakage oil. It's still going to close off the P port, most likely, definitely if you have a positive overlap, but it's still going to, you're going to actually be able to see it once the push button is being pushed out there. So that's one thing to keep in mind. And that is something that's going to happen, because since you already from the start with a slide valve, you are going to have leakage. Then the older the valve is, the more it has been used, and the more wear and tear it's been subjected to, then the more leakage you are going to get in it. So it's very old valves can be a problem with too much leakage. And that also counts for leakage between the pressure ports and the A ports when you're running it. So that so even though you have it closed, you can start getting some flow through it. Same goes for the Poppet valve. When you activate it, you get full flow between the P and A ports. You can see there's a bit of a different design on the pilot side here, so that you are actually allowing some fluid, room for some fluid there. You're not pushing the piston all the way to the end. Exactly why they have it on the Poppet one and not on the pressure port, I'm guessing that the Poppet one has been designed to close completely without leakage, and it's going to close very quickly. So they want to avoid the problem of trapping some leakage oil on that side, so that they give it a chance to go all the way to the end. And then when it's activated, you get full pressure through. And for the Poppet valve, it can also be placed, looked at like this, basically, by saying that the Poppet itself here, if we are getting flow from A towards P, if that flow gets high enough, you can actually start moving the Poppet, so that if you get high enough pressure on A, you can actually open it up and get it back, so that you basically have a non-return valve on P, so that P won't be able to enter the valve, but A can actually run through if there should be a problem. But this using this symbol is very. I think I've seen it only once in all of the hydraulics I've ever seen. So it's something that's very seldomly used. So the usual one is this one where the ports are just closed. So depends. I guess it can depend a bit on what supplier you're using, how their engineers view the valve. And of course, you can also get them as normally open, whereas this would be the normal position. So you would instead have a spring on. You would instead have the spring on this side, and you would have the push lever on this side, so that you would have to push it in order to close it. And these are used for single acting cylinders, as I mentioned a bit earlier, but also for bypassing. So for example, if you have a bypass filter where you don't necessarily use the bypass filter all the time, you can just go in and manually run a certain amount of fluid through the bypass filter if you want to. You can also have it mounted close to, like the valve we were looking at before the break, which was closed in the center. So instead of having it being able to circulate when it was closed in the center position, then you can have one of these mounted and make it possible to just bypass this one and send the fluid back to tank. So that in an emergency where you couldn't run this valve, you could have an operator come in and just push the button and maybe have a detent instead of a spring on it. So they could push the button and activate it, and then you would just have circulation between the pump and tank. So it would just run the fluid until you got time to fix the valve that was broken. And you also use it to open and close flows. So and also in sequence valves, which we talked about in the subsea industry, when you are using different levels of pressure to open more and more parts of the systems. So then you can use valves like this to open it up. And then you can control a motor in one direction. So you can switch direction for the motor, anything like that. You'll need a more advanced valve then. But just for starting and stopping a motor, that's possible with a valve like this one. So say for an example, you have a circular saw that you're running with a hydraulic motor. Then the saw blade can only saw in one direction. If you run it in the other direction, it's not going to cut. So then a valve like this one would be possible to use, because then when you activate it, the saw is going to go in the correct rotation, and when you stop actuating the valve, the motor doesn't get any more flow and it stops. So then we're going to look at a stem actuated 2-way valve. So this will be a mechanically actuated one. And it is often used to regulate volumetric flow. And it is, of course, mechanically actuated. And it can be converted into several neutral positions, so that you can have a bit to choose from there. So this one has a roller at the end because it has a ball bearing. So why they are calling it stem actuated in this case, I'm not quite sure. They're calling this part in here, that's the stem. So you could have had the stem just going all the way out and be activated linearly. But in this case, they've put a ball bearing on the end so that they have a roller instead. And then between the stem and the rod, between the stem and the piston, we have the piston rod coming up. And then, of course, we have the piston itself. And we have a spring disc and a spring at the end here. So the spring disc is just to keep the spring in the correct position so that it can't bend to the sides or anything. And this would be the symbol for it. In this case, it is normally open between, it normally has pressure between the pump and the components. So that's the neutral position. And then it's the spring that's pressing the piston all the way to the end. And then if we actuate it, the ball bearing is going to start rotate against whatever it is that's actuating it. and it's going to start being pressed inwards. So the stem is being pressed against the piston rod, and the pistons are being moved. The spring is being compressed. And in the end, this part of the piston is going to shut off the flow there. So then it stops completely. And as you can see, this is actually a 4-2-way valve, because you can see we have more openings here, but these ports are blocked off. So they basically used a more complex valve, and they've just blocked off ports in order to use it in a more simple manner. Then we have 3 2-way valves. So now we have 3 ports. So we've added a tank port to it. So we have pressure port, component port, and we have the tank port, which will just be returning fluid to the tank. And this is a typical symbol for it, where we have in the neutral position, the one we can see up here, our pressure port has been blocked off, so that one is closed, and we have free access between the component and the tank. So it's basically returning fluid to the tank from the components in the neutral position. Yeah, P is blocked. And then if we actuate it, so if we push down the push button, then the tank part is going to be blocked, and we're going to get flow from P to A, because then we're going to open up the P ports. And of course, you can always get it as normally open, which just means that you'll be switching places on the two blocks there in the symbol. And uses for it is actuation of single acting cylinders and also switching shunts. And a switching shunt is basically when you want to switch a flow through something else. So if you need to very quickly change the flow rate, it wouldn't be these are throttle valves, so they limit the flow rate to a certain volume. So this one is set to 2 liters per minute, and this one is set to 4 liters per minute. And what happens is that you could have just one of these, and then you would go in and you would manually adjust it from 2 liters to 4 liters. But that is going to take a little bit of time, and you can't. They usually operate with an adjustable knob, so that you turn the knob, and then you have to sort of wait until you see what the flow rate is going to be. So it takes a little bit of time to adjust them, and especially to get them exactly right. But if you instead have one set for 2 liters, one for 4 liters, and then you can use one of these valves here as a switching shunt and place it in here. So that if you want 4 liters per minute, you leave it in the neutral position. If you just want 2 liters per minute, you activate the valve. Then you switch it straight over to the other one, and you're going to throttle down the flow a bit so that you get a more fitting volumetric flow rate. The same happens in this other part here, where we have that's a cooler. So it looks a bit like the filter symbol, but since it has arrows going out to the side, it means that you are extracting heat from the hydraulic fluid. And this one is a heater, because it has arrows going into the center, so you're adding heat to the hydraulic fluid. So this one used as a switching shunt. Here you have it solenoid operated, so the solenoid is probably connected to a temperature sensor, which reads off the temperature of the hydraulic fluid in the tank, most likely. And then it's going to start switching between cooling and heating, just to keep it at a very constant temperature at all times. So then you also just switching back and forth between 2 different flows in it. Yeah, the heater and the cooler. Yeah, so then we're finished with Friday's lecture. We're almost finished with today also, but I think it was important to do this a bit more thoroughly to get everyone on the same page. So we looked at directional control valves on Friday, all of these different symbols and ways of showing them. And we looked a little bit at the port options that you can have, that there are different kinds of them. And we became familiar with the different actuation methods today. We looked at that. And we also looked at how the solenoid actuation works. And we've also looked at the results of a power failure or a wire break in the solenoid. So how can you design your solenoid to act the way you want to if you lose electrical power to it? And then we've looked at 2 two-way valves and 3 two-way valves on this one. And we had 2 YouTube clips that we saw on Friday. So then we'll start on today's lecture, which we have no hope of finishing today, but we'll just start on it at least, and we'll continue on Friday. So this lecture is to become more familiar with 3 two-way valves. So we started on them on the previous one. We're going to look a bit more on 3 two-way valves. Then we're going to look at 4 two-way valves to get more on that. And we're going to learn about the connection between the transitional positions and overlap. So that how can you basically, when you're switching from one position to another one, there is going to be something that's happening inside between those. So exactly when the piston is moving. And the overlap is what determines what's going to happen. So we're going to look more at that. We're going to get to learn more how the tent works. We're going to look into detail how it's designed. We're going to look more at 4 three-way valves. And that's it for this lecture. So we'll start off with the 3 two-way solenoid valve. This one has a spring return. And it doesn't have pilot operation. It's directly actuated. Yeah, so the valve piston is actuated directly by the solenoid. We don't have any pilot amplification on it. So this is a typical solenoid valve, where you can see the valve itself isn't really big, but you have the solenoid part is just as big as the valve housing. So it takes some room with all of these electrical coils that you use as electromagnets. That's basically what this area is, just loads and loads of copper wire that's been coiled, creating an electromagnet. And in this case, this would be the symbol. So we have 3 ports, P, A, and T, and we have 2 switching positions. So either letting pressure go from P to A or letting flow go from A to T. And the solenoid in this case is called M1. That's going to actuate it. But it also has a manual override, as you can see. So it's put in a push button there. And that means that it's possible to actually, it's not been drawn into this figure, but it's supposed to be a push button on the outside here, so that you could push it in if needed. So we have the stem here, the part that's going from the pistons and into the solenoid. And we have a spring disc. And then we have the piston in the middle. And of course, the housing around everything. And we have the spring over at the end there. And as I mentioned, these are the solenoid coils that are going through it. And then we have what is called the armature. And this is what's going to react to the electromagnet. So that this is basically a magnet. It's not a permanent magnet necessarily, but it's a material that's going to become very magnetic once it's subjected to the magnetic field of the electromagnet. So it's going to start moving. So when you start, when you send electrical energy into these coils, they're creating these magnetic fields around them, and that's going to start moving this whole part here over to the end, over to the side. And then we have the manual override over on the end there. There should be a push button on the figure there. And this one was when it's normally closed, and now it's been actuated. So the spring has been compressed on this edge, and we have opened up flow from the pressure to to the components. And as you can see in this one also, we don't have a separate leakage line, but we have this side of the piston is connected to the tank side of the piston. So instead of having a separate leakage line, since we have this tank line going in, we just allow the leakage to trickle back into the tank ports. So in the neutral position, which is here, normally closed, A is connected to the tank, and the P port is closed. And then when we actuate it, we get P to A and T closed. And this is called a wet solenoid. And what that means is that it's not, there are no sealings between the valve itself and the solenoid parts. So all of this is filled with hydraulic fluid also. So this armature part and the stem and everything, it's floating in hydraulic fluid. And all of it is connected to the tank port side, as you can see. So that's, there will never be a pressure buildup in there or anything like that. It's just basically floating in the hydraulic fluid. Which, so long as your hydraulic fluid is oil, unless it's one of those flame retardant ones with a lot of water in it, that's going to be very good, because then you've got metal parts that are covered in oil so that they won't corrode much. Because usually the hydraulic oil has good corrosion resistance properties. So it's basically just protecting the internal parts of the solenoid from corrosion. Then we're going to look at 4 two-way valves. And now we have pressure, we have tank, and we have A and B ports. We also have a leakage line. Because now we have the problem that no matter how we are actuating this one, since it only has 2 switching positions, one of the ports, A or B, will always be connected to the tank, which means that you can get pressure going through the return line. For an example, if you have a cylinder with a hanging load in it, that's going to be pulling on the cylinder, and it's going to create a pressure on the return line. So you really don't want pressure having the chance of escaping in here and coming to the other side of to the spring chamber, basically, because that's going to interfere with when you're actuating your valve. So that's why we have a separate leakage line for these. Yeah, basically what I just said. And in the neutral position, once the spring is fully extended here, we have connection between P and B, as we can see here. The arrow is going straight from P to B. And we have connection between A and T. So the arrow is going straight from A to T. And if we are actuating it, so we are pushing on the button, our flow will start going from P to A, or this arrow here, and we will have flow going from B to T also along that arrow. And if you're going to use a valve like this, it's going to be a simple design, so long as it's a slide valve, because it's basically going to look like this. If you're going to create it as a Poppet valve, it's going to be very complex. You're going to need several Poppet valves working together in order to be able to create the same effect as you get from that one slide valve. It is also possible to use just 2 pistons instead of 3. So in this one we have 3 different pistons along the piston rod. And if we have just 2 pistons, we don't need leakage oil ports. But that also means, as I said, we can have we need to specify a lower maximum pressure for the tank ports. So for our return line, we can't handle that much pressure on it. So again, it depends a bit on how the system is going to work. So you see that basically the tank port is connected to the spring chamber completely on that one. And applications for valves like this is for double-acting cylinders and controlling those. So it's very, very useful for extending the cylinder and retracting the cylinder. So it will go, whether you're actuating the valve or not actuating the valve, the cylinder will go in one direction or the other direction. So it's very useful for those. And you can also control motors in both directions, sending it clockwise or anti-clockwise, if the motor can go in both directions. It's not all hydraulic motors that can go in both directions. And you can control two circuits with it by using A and B. So that's another possibility. If you have B circuit running off to doing something else in the system and the A circuit running off to doing something completely different in the system, then it is possible to switch between them, because especially if A is doing whatever work it's supposed to do, then B is not going to do anything, so it just returns to tank. So now we get to the transitional positions. And those are very important for selecting our valves, because we need to know how is it going to act when we are moving the slide back and forth. So in a 4-2-way valve, the transitional position won't be an actual switching position. And that's why it's going to be shown here in a while, but I'm just going to show it here also. Even though it's a 4-2-way valve, you might draw it with 3 boxes, but you'll make sure that the middle box has a dashed line, because that tells you that when you're switching it, you're going directly from this position to that position, but whatever position is in the middle here, that's what's going to happen when you're moving the slide. So as long as the slide is actually moving, that's the function it has, but when it's in the end position, it's this function, and in the other end position, it's that function. Yeah, and it's a result of the overlap. So if we have positive overlap on our pistons, then when we are changing switching the valve, then all the ports will be blocked, just as we are moving the slide. So for a brief moment, it's going to block all of the ports, which means that with a positive overlap, you have the potential of getting pressure peaks, because for a brief moment, you are blocking off the pump ports completely, so that the pump is just slamming all of the fluid it's pumping. It's just slamming it against a wall, basically. So it's just full stop. It's not going to last for very long. As you saw with the solenoid valves, we're talking about milliseconds usually. Maybe you're up to half a second or something if you have a lever that you are manually operating. But it's not for a long while, but you can get pressure peaks from it. However, if you have a negative overlap, then you have full connection between all of the ports, which means that you're actually going to lose your pressure for the brief moment that you're switching between them, which can be good if you're in a situation where you really don't want any pressure peaks in your system. Then it's better to actually lose a little bit of the pressure until you get the slide all the way across to the next position. But that's basically a part of you really need to see what the function is. If you're supposed to run a cylinder, and it's very important that it stays in its for example, if you run it all the way out to its end position, and it's very important that it stays in that end position until you actually tell it to come back, then this one wouldn't be all that good, because when you're releasing the pressure, you lose the pressure in your cylinder, and then you have to build it up again. So for a little while there, you're going to lose a bit of your control over the cylinder. Then it would be better to have a positive overlap, because it would be better to have a pressure peak than actually lose control of your cylinder for a short while. But if losing control of your cylinder really isn't a problem, then that will be, the negative overlap will be more easy on your system, basically. So you really need to see the full picture when you're working on it. And then we're going to look at one lever valve with spring return for 2-way. So it basically looks like a gear shift in a car sometimes. depends very much upon the valve itself, how it's going to look, but sometimes they look like this. So you have the piston in the middle, of course, a spring over on this end. You have the stem part over here, and you have the slide here. And then we have the lever itself going up here, and it's pivoting on this point here. So it's fixed on that point, and it's going to pivot across it. So you can see that you're getting quite a lot of lever arm up here to where your hand is, compared to what you're getting down here. So the force that you are applying to the lever is being multiplied down here. So you're getting a lot more force on the slide itself than what you're actually giving the lever there. And if it's a four-way valve, so of course it has 4 ports, 2 working ports, 1 pressure port, and 1 tank port. And this particular one is normally sending pressure from P to B when it's in its neutral position. And this is the neutral position. Then we have it's going straight up, so the lever is basically going straight up. It's not activated at all. And then it's the spring that is actuating the valve itself. And we get the flow from P to B and from A to T. But then we can switch it so that we can basically pull on the lever so that we get it into the 1 position. So we just pull it a little bit back. Then we're actuating it. And we get flow from P to A and from B to T. I think we'll do this slide and then we're stopping. So we're going to look at a 4-2-way double solenoid valve, and this one has a detent. So we have a manual override on one side. We've got the armature in there. We've got the solenoid coils around here. And it says armature here, but of course it's supposed to be the stem because it's this one. So that's an error in your book that it says armature on the 4th part there. It's supposed to be stem. You'll see in all the similar figures beforehand and also afterwards, it says stem always on that location. It's never armature there. So it has to be an error. Then we have a spring disc. We have the piston in the middle. And then over here we have the detent. And then we of course have a solenoid over on this side also, which is the same as on that side. We have A and B ports, pressure port, and tank ports. And these are also wet solenoids, so they are the solenoid parts are filled with hydraulic fluid. And we have the M1 solenoid on one side, M2 on the other. We have the detent, which will hold the position of it, but we also have manual overrides on both sides. So we have the possibility of manually overriding it if we have a power failure. So if we briefly energize the M1 solenoid, so we just set electric current to it for a short while, then it's going to switch over so that we get flow from P to A and from B to T. And then the position is retained by the detent, so it's keeping it there. So we don't need to apply the electrical current to M1 at all times in order to keep it there. We just need to give it a boost so that it switches over. And once it's done switching, those 20 to 90 milliseconds, whatever it takes to move it, then after that we don't really need the electric energy going to it. So then we can just let go of that one, and the detent is going to keep it in place. So then we can briefly energize M2, and we're going to switch it so that we get flow from P to B and from A to T. And again, the position is kept in place by the detent. So on Friday, we're going to look at how the detent works. So we're going to start off with that on Friday.